Well, my friends, this is it. This is the last lecture of the course. This is the second lecture of Unit 12, and I'm not going to do anything new. You'll be relieved to find out what I'm going to do is a review of everything that we've covered up to this point. So I'm going to just start at the beginning, go through the topics unit by unit, and try to give you some guidance about what are the key concepts, what are the key things to take away from the course as you prepare for your final exam. So thank you for tuning in. I hope that video lectures have been okay. It's a different experience for all of us, but we've got through to the end of it. So let's finish up and get you ready for your final exam. So in this lecture, I'm not going to reteach the whole course. I'm just going to survey the topics that we have walked through and try to give you a big picture of the whole thing. So we started in Unit 1, and we talked about a few simple ideas. Types of data. So that means cross-sectional and time series. Those are the two types that we mainly worked with, cross-sectional time series data. We talked about some transformations that are sometimes useful when you're preparing your data set, types of graphs that you can draw, and then we introduced the principle of estimation, where estimation means taking the data set and picking the best values of the parameters for your model. So picking the best values of the parameters for the model. And this notion of best means optimal. And so if it's an optimum, that means you're either maximizing something or you're minimizing something. And most commonly, we use the criterion of minimizing the sum of the squared errors, which is the least squares rule or principle. And then at other times, we also looked at the maximum likelihood rule. So those are both estimation rules. They give you estimators. There's an estimator that minimizes the sum of the squared errors, and there's an estimator that maximizes the probability that you've got the right estimator. Fortunately, both give you the same answer in the case of ordinary linear regression. And we talked about some descriptive statistics. Things like the mean squared error, variance, standard deviation, the concept of a sample versus population. So we only ever work with a sample. We use the statistics on the sample in order to estimate the parameters of the population. Expected value. We saw an example of expected value as a weighted average, where the weights are based on the probabilities of that particular value. And then we also used it as an operator later in the course, a mathematical operator. So the idea there's an expected value of our coefficient estimate beta hat, and if the expected value equals the true value, then you have an unbiased estimator. That came later. And then things like variance, correlation, and covariance. So basic tools, statistical tools for our course. And then Unit 2, we jumped right into simple regression, where we have a linear model like this, yi equals x beta plus e. And when we write a simple regression model with no constant term, that means y and x both have to have a mean of 0. So you can ignore the constant term if you have a mean of 0 in both the y and the x values. So that's what lets us write the regression model in this form, and then that form is convenient because there's a whole lot of formulas that are really easy to use and to work with. Then we talked about the least squares rule to estimate beta. We used a picture, like a scatter plot of the data, and the least squares rule gives us the line of best fit through the data. So beta would be the slope of the line here, and that's x and that's y. And the least squares rule minimizes the sum of the squared deviations around the regression line there. And then you've got various measures of the quality of the regression, measures of the fit. So we have the sum of the squared residuals, the total sum of squares, and the regression sum of squares. And then we have r squared, which equals the regression sum of squares over the total sum of squares, or 1 minus the sum of the squared residuals over the total sum of squares. And so it's measuring the fraction of the variance of the dependent variable that is explained by the regression line. It was at this point that we also introduced confidence intervals and hypothesis tests. And briefly introduced T and F statistics. So we actually covered quite a bit in that unit, and also p-value. And so that was simple regression. And then we went on to Unit 3, although we were still in Chapter 2 at this point, but we went into Unit 3, and this was an intro to multiple regression. So we talked about the idea of the linear model. So all the regressions that we estimate are linear functions. And then the choice of variables to include, well, we had to think about the problem of omitted variable bias. And multicollinearity. So when you have two explanatory variables that are so perfectly correlated, they're not giving you distinct information. And then we also introduced the idea of dummy variables. So just binary variables, 0 or 1. And so this was the intro to multiple regression, and also the introduction to the whole notion of model building and selecting the linear model. In Unit 4, we began looking at some of the theory behind regression. So this introduced the assumptions behind simple regression, which would carry over to multiple regression. Whoops, can't talk and write at the same time. Assumptions behind simple regression. So this required us to talk a little bit about probability distributions, in particular the standard normal, and then related distributions to the standard normal. So chi-squared, t, and f distributions. And I made a point here that isn't in the chapter, but it's that statistics that are chi-squared can be derived as functions of standard normal, and so can t and f statistics. So essentially the issue is that if you have one variable that follows a normal distribution, and then you have another variable, say z equals some function of x, then z doesn't necessarily follow the standard normal. It follows a different distribution based on that function. And so if, for instance, z is x squared, that's a chi-squared distribution. And there are other transformations that lead to the t and the f distributions. And then, but what we spent most of the time talking about were the classical assumptions. Okay, that list of assumptions about, so the errors have a mean of 0, they have constant variance, there's no autocorrelation across the sample, you know the list. The x's are non-random, and that the errors follow a normal distribution. So that was Unit 4, and then Unit 5 began talking about what are the implications of these assumptions. So the implications of the classical assumption so that one of them, a very important one, is the unbiasedness of our least squares estimator. And then the distribution of beta hat under the classical assumption. So if classical assumptions are true, then we know something about the distribution of beta hat. The Gauss-Markov theorem, a nice mathematical result that tells us that if the classical assumptions hold true, then out of all the linear estimators, all the linear unbiased estimators that we could choose, the least squares estimator gives us a distribution with the smallest variance. So it's a nice property. It means that we're making the best use of the data, we're making the best use of the information in the data set. And you want to make sure you know what blue stands for. That's associated with the Gauss-Markov theorem. And then one of them we talked about, didn't really pursue very much, is the idea of maximum likelihood. So I mentioned a few minutes ago that when you're picking the best estimator, you're either maximizing something or minimizing something. You're maximizing a good property or minimizing a bad property. So in the least squares rule, we're minimizing the errors, the sum of the squared errors. In maximum likelihood, we're maximizing the chance that we've got the right parameters. And fortunately, under the classical assumptions, both approaches give us the same answer. So we tend to learn least squares in econometrics, partly because it gives us an unbiased variance estimator as well as the unbiased slope estimator. And partly because it's just a little easier. It's more intuitive. You can start with least squares, but if we started with maximum likelihood, it would be a real uphill battle on day one to get the intuition. But when we go on to other applications of econometrics, maximum likelihood is sometimes easier than trying to find a least squares estimator. All right, Unit 6. in Unit 6, we went back over some ground that we had already approached before, confidence intervals and hypothesis tests. And so that's where we looked at the rules around manipulating inequalities and then constructing those probability statements, so that if you're told a variable x follows a certain normal distribution, what's the probability that x falls within a certain range? And this in particular applied to confidence intervals for our estimate on beta. So that the interval that we think we've got a 95% probability that the true value of beta lies in that range. And then hypothesis testing. And the most common hypothesis test that we do is test the null that beta equals 0. So if you want to test the null that beta equals 0, you can use the t-statistic. So you should know that by now, that okay, if that's a hypothesis test, if that's the null hypothesis you're interested in testing, you use the t-statistic to do that. And that brings up, when we use t-statistic rather than standard normal, modification when sigma squared is unknown. All right, so when we have to use an estimate of sigma squared rather than sigma squared, if we knew sigma squared, we could use the standard normal tables. We could construct our test statistic for that null hypothesis using standard normal tables. But we have to estimate the variance. So then we need to adjust the distribution of our test statistic to take account of the fact that we're using an estimate of sigma squared. And that's why we use the t distribution rather than the standard normal distribution. Now, if the sample size gets large enough, the t distribution eventually converges to standard normal. But for smaller samples, it can make a difference in the location of the critical values. Unit 7. So, and just going back to this, when we are taking account of the fact that we're estimating that variance term, these confidence intervals are going to get a bit wider, and the critical values get a bit higher, which means it's harder to reject the null hypothesis. All right, Unit 7, back into the topic of multiple regression and hypothesis testing. So we reviewed the classical assumptions. And we talked about hypothesis testing again. And we talked about the choice of variables. So I went through that again. The pros and cons of including another variable in your model. And then we also did testing linear restrictions. And so that was the idea of testing maybe two coefficients in the model, whether they have the same effect, whether they're equal to each other, or any other form of a linear test that we wanted to choose. And you remember that our test score is based on, does the sum of the squared residuals change very much? And so we did it. We looked at the actual formula and then also learned how to do it in R. Unit 8. Here we took a bit of a detour to talk about functional forms. And here, this is because what we're trying to do is estimate a model. And we're trying to construct a model that will pull the information out of the data set that we're interested in. And so We talked about a few things like linearizing equations, like using logarithms, and adding quadratic terms to get curvature in the function. And an important topic was interaction terms. Interaction terms. So when you have one thing multiplied by another, and we put those in so that we can have the marginal effect of one of the variables dependent on the value of another variable. And we did that with some dummy variables. And so we looked at examples of how you can use dummy variables to look at whether groups differ in the data set. I always had some examples of that. So that kind of brought us to the end of the basic concepts of regression modeling, of constructing a linear model with linear regression tools. And then we started looking back at those classical assumptions and saying, okay, what happens if the classical assumptions don't hold? So we started with heteroskedasticity. And so this is the violation of the assumption of constant variance. And as we talked about what it is, we talked about testing for it, and we talked about corrections. So one approach is GLS, doing a weighted least squares model, where you try to put in a counterweight to the process that's driving the heteroskedasticity, or you can use the heteroskedasticity consistent heteroskedasticity consistent estimator, HCE, White's matrix. And so that was the procedure for dealing with heteroskedasticity. Unit 10, it was the topic of autocorrelation. So again, we talked about the violation of the classical assumption. So what happens if that assumption of no covariance between adjacent or no covariance between two error terms at different points in the sample? So what happens if that classical assumption is violated? And again, we talked about tests for autocorrelation and remedies. So one was the Cochrane-Orcutt. So it's a GLS model using quasi-differencing of the data. And if you have an AR1 process, then that'll give you an efficient remedy. But then the other option is the HCE type Newey West estimators. And so we could call that one ACE, autocorrelation consistent estimator. But what's more common is just to use the term hack. I don't know if we use that during the course. I don't think it's in the textbook, but this is what people use now just to mean either one of these, heteroskedasticity and or autocorrelation consistent estimator. So we have a hack for how we deal with these problems. Okay, Unit 11. So this was the topic of endogeneity. and instrumental variables. And so we talked here about the violation of the classical assumption. So in this case, it's the assumption that the x's are fixed, non-random. If that assumption is violated, then we have the problem of bias and inconsistency. It's a real mess. Can severely bias the coefficients. So when we're talking about what to do about it, one of the topics that we came up with was probability limits, or PLIM. So a consistent estimator is one where the probability limit is the true value. An unbiased estimator is one where the expected value is the true value. Probability limits are interesting tools. It's sort of like an expectation, except it does allow for biases in small samples, but it does mean that as your sample gets larger, your estimator not only is unbiased, but the whole distribution collapses to a single point. So consistency is a good property of an estimator, as well as unbiasedness. So probability limits, we talked about the IV estimator, and this requires you to have instruments, and good instruments are uncorrelated with the error term, but correlated with the explanatory variable. And so we talked about how you go about trying to identify and choose an instrument in the model. And in your assignment, when you looked at the schooling of the mother and the schooling of the father, that's an example of an instrument because it's exogenous, it's determined outside the model, so it shouldn't influence the size of the error term, but it correlates with the education level of the person in the sample. So that was the instrumental variable approach, and then we talked about how these issues can arise. One is measurement error, and one is endogeneity. And so we talked about endogeneity, meaning the value is determined inside the sample, and as far as testing goes, the Hausman test is the method that we use to figure out if we have a problem of bias or inconsistency because of endogeneity or measurement error, and then whether we need to apply instrumental variables or not. So that was Unit 11, and then Unit 12 was our discussion of matrix algebra. What do I need you to know coming out of that? Well, I need you to know so here are the things that I want you to know. Checking if matrices are conformable for multiplication. And then dimensions of a matrix product. What does that mean? Well, let's say I've got the matrix A times the matrix B equals the matrix C. And if I know the dimensions of A and B, I should be able to figure out the dimensions of C pretty quickly. So that's something I expect you to know how to do. That if A is n by k and B is k by 1, you should be able to see at a glance that C would be n by 1. And then our least squares estimator, our ordinary least squares coefficient matrix, beta hat, is X transpose X inverse X transpose Y. And by the way, you don't need to know what I'm about to tell you now, but if you're wondering why that package in R is called sandwich, why is it sandwich to get White's residuals? Because the formula for the variance estimator, if you're going to use White's method, is X transpose X inverse X transpose omega X, X transpose X inverse, where omega is formed using the residuals of the OLS equation. So in particular, it's got the squares of the residuals down the diagonal. And so this kind of expression shows up in a bunch of places in econometrics when we're constructing variance estimators. And so it came to be called a sandwich matrix. So you've got a piece of bread, and you got a piece of bread, and you got the filling of the sandwich. And, oops. Yes, that's right. So that's why the package is called sandwich, because it estimates a whole class of sandwich estimators, namely all the variance estimators that can be constructed in this form, where you're just substituting different versions of omega in to deal with different problems of violations of the classical assumptions. Okay, but you don't need to know that. So if that stressed you out, I'll just put my hand right there, and you don't have to know it. But you do need to know that the variance of beta hat is sigma squared X transpose X inverse. We didn't derive that, but that is the case if the classical assumptions hold. If the classical assumptions hold, that's the expression. If classical assumptions don't hold, then it takes that form. But all right, so there's your review of the topics, and good luck in your studying, and I hope you do well on the exam, and hope you enjoyed the course, and I will not be talking to you next week, but good luck in the exam.